Okay, so this question is from the 2008 HSC, and it is question 12a. And the first thing we have to do, I've transferred the information from the question onto the board. The first thing we need to do is we need to apply a load of, well, we've got a mass of 50 kilograms. Now, at this point, that should be fairly obvious to you that the force that will be applied due to that mass is mass times gravity, which equals 50 times, now we're allowed to use in the HSC, we're allowed to use 10, right? We really should be using gravity as 9.8, but for our purposes, to keep things easy, we're going to simplify that and we're just going to say that 50 kilograms is 500 newtons. You'll find HSC questions that use 9.8 and 10 interchangeably. In physics, you want to stick to 9.8. Professional engineers will always use 9.8, but you're allowed to use 10 for the sake of convenience in these situations. Okay, now the first thing we want to do, well, okay, so the question has asked us specifically to find the horizontal and vertical reactions at, horizontal reaction and the vertical, oh, it's a port A. So they have labelled that location as, use purple for the locations. So that's point X and that's location A. So they've asked us to find that reaction. Now, we can just start straight away with that, which is probably recommended if what we want to look at as well is the next part of the question says find XY, find the force. It tells us straight up that it's a tensile force, so they've made that easy for us. They tell us there's a tensile force in member XY. So the question we can say is, if we're going to consider XY, do we even need to find reaction B? Typically, I tell you guys to start and find the pinned reaction first. That's what I usually tell you. Find the pinned reaction, because the pinned reaction is simpler. It only can have one force, which we know is going to be, the force is going to be going perpendicular to the reaction, right? Now, in this case, we also know that we're going to have a reaction. Well, presumably, we have a reaction. We could presume that it's going to go that way. Now, I can tell you straight away that it's not, right? Because intuitively, we're going to get there, but it's not going to go that way. But for the moment, let's just say that we make the assumption that usually reactions are pushing out, and so we're going to try that assumption. Now, also, it's going to have a vertical component, because pinned reactions have both a horizontal and a vertical component. And I can see, well, there's only one other vertical force in this diagram, so in order to balance that vertical force, I'm going to need to have, well, I've jumped a little step there, but I've told you that that reaction is going to be going there. So let's see how we go with that. So if we're going to find this member, XY, we don't really need to find this reaction. We can just look at the right-hand side of our truss. And so if that's the case, we can skip having to find reaction, we could call this reaction B, right? We're gonna label it as reaction B, but we can actually avoid finding reaction B at all. There's no need to find reaction B, even though typically we would find reaction B. In this case, we're not going to do that because we don't need to. We want to save ourselves a little bit of time. I realize I've just taken enough time that I could have found reaction B in the time I explained why we're not finding reaction B. But the whole point is that I want to convey to you that we don't always have to find all the reactions. Okay, so what we want to find here is this. Let's explain first of all, how did I come to this conclusion that the vertical component was going to be up? How did I come to that conclusion? Well, how we came to that conclusion is I used this formula, the sum of the forces vertically equals 0. Now I look at my diagram, and now I'm establishing a convention. I always use the convention that up is positive. Sometimes people do use down as positive. That's not what I do. Okay, so if we look at this diagram, before we know this value, if we look at this diagram, there's only 1, 2, 3, 4 forces on the whole diagram. And that's if we break up reaction A into two parts. So if we look at this diagram, what I like to do is I just typically like to say, well, let's just draw a picture of all the vertical forces. So I have 500 going down, It's not the world's best 5 because I wrote it on the side. 500 going down. So to balance that, I'm going to need some amount of reaction AV. There's no other forces there. So we know that RAV has to equal 500 newtons up. There's no other alternative. Now, if I was going to write that mathematically, where I always like to draw for vertical forces, or sorry, for the leftover force, I just draw a little diagram. But how we can write that is we can say, okay, I'm just going to write it to the side here. 0 equals, now I said 500, right? 500 is going down, so I have to write a minus sign because that's my assumption. Based on the convention that I've said positive is up, I'm going to write minus here, and then I'm going to say plus, because I'm assuming that this arrow is going to go up, plus RAV. What happens is when I then take this equation, I rewrite that, I have to add 500 to both sides. I get 500 equals RAV. Now my assumption was that RAV was up, right? I assumed it was up, therefore positive. It was positive, therefore my assumption was okay, therefore it's up. So I write RAV equals 500 newtons up. Okay, we all okay with that so far? Cool. I'm going to list that, I'll remove that and I'll just leave the 500 as up on the side. I don't need that there anymore either. That's taking space. Okay. I'll just write, as our note, I'll write RAV equals 500. Now, what we next need to find is RAH. To find RAH, we don't have any way of figuring that out. That's an unknown to us. And we have two unknowns in this equation. But the magic of moments is that when you multiply something by 0, it's 0. And we can know that. So even though we have two unknowns, if we multiply this force by 0, we don't need to worry about what value that is. It could be 10 billion, it could be 6 trillion, doesn't matter, because if it multiplies by 0, we can ignore it for our equation. That's the magic of moments. That's why we use the moment formula. Now, to make that multiply by 0, the 0 is the perpendicular distance. It means that we have to make the point where we measure all of our moments from be 0 millimeters from this force. And the only way we can do that is by choosing a point that this force passes through. And this force passes through B. It also passes through this force here. It also passes through Y. But if we choose B, that's the obvious place where this force is passing through B. So if we take moments about B or Y, right, that force, it's going to have 0 perpendicular distance. If it's 0 perpendicular distance, the moment gets multiplied by 0. It means we can ignore reaction B. So I'm going to label that just so that we have a reference to refer to this as. We're going to call this here RV. But that's just for the sake of our formula here. Okay. And I'll label this one here as well so that we have a reference to refer to it as. We're going to call this one RAH. So, our formula is going to look like this. First of all, I always use clockwise as positive. Right? At uni, you might find that 50% of the time you don't use clockwise as positive. You look at the HSC answers, sometimes they don't use clockwise as positive. Me, I just decided when I started teaching, I'm always going to use clockwise as positive. Now, the next thing I'm going to say is the sum of all the moments are 0. And that's true anywhere. If this thing is in equilibrium, it doesn't matter where you measure from, the sum of all the moments is going to be 0. But we're going to choose to take all of our moments from what location in order to make the perpendicular distance 0? B. Okay, so we're saying the sum of all moments measured from point B, or end point, but we're going to say that all our moments are going to be measured from point B equals 0. We're setting clockwise as positive. So I write 0 equals, and then I just label all of my forces. Now I'm going to write this one in green to indicate to you, you don't need to write this, and you won't see this in the textbook or in past answers, but I'm going to write RB multiplied by 0. Yeah? That's why we do moments, is so that I can eliminate RB. Then I go to the next force. I'm going to say, well, okay, the next force here is RAH, and it is relative to B, the perpendicular distance is 1,000. Now, rather than writing 1,000, I'm going to use meters instead of millimeters. So I'm going to use, now it doesn't matter what units I use. I can use any value I want. I can use X, I can measure things in cubits, I can use whatever measurements I want because they will end up eliminating, they'll cancel out in the equation. So we don't need to worry about that. RAH. The next force is RAV. What is the perpendicular distance of RAV?
0.
0, excellent, thank you very much. Because that line passes through, it's actually being applied here. Even though I've drawn it here, the force is actually being applied here, and it's going to pass through that same location. Right? That's a bit of a confusing thing for people, and I'm glad you answered that. Right? There's a force, that force, even though I've drawn it here, it's actually going through point A. And so point A lines up with point B so that it won't have any perpendicular distance. Excellent, thank you very much. Okay, there's only one other force here, which is Y, which I'm going to write as 500, and the distance from 500 is 2 plus 1. Now to simplify that, above I'm going to write 3. Okay, so our answer is going to be 0 equal, oh, now you'll notice, sorry, before I get too excited, I just wrote minus, minus, minus. I wrote minus for everything because I have not yet assigned directions for anything. Okay, for RAH, relative to point B, if I put the center of my axle on point B, and then I push it in the direction that I've assumed RAH is pushing out. I've assumed that. They didn't tell me that in the question. I assumed that it was pushing out. And so if I assume it's pushing out, it's going to go what direction? Clockwise, right? So if it's clockwise, I need to turn that into a positive. RAV is 0, so it doesn't matter. We can just leave that. Minus 0 plus 0 doesn't matter. Okay, 500, again, if I put my finger on that, I get this direction, this moment. So I'm putting the center of my axle as B, because we're taking moments about B. And if I could put my force, it's going down. Down relative to B at that location gives us clockwise moment. Okay, so what have we got here? We've got 1 RAH, which 1 RAH is, I might as well don't even need to write the 1, but I will just to indicate. And then we have plus 1,500, right? Gives us our value. Now, what we need to do is the same thing we did before. We're going to take minus RAH gives us minus RAH equals 1,500. Now, we don't need to do any division because it's dividing by 1. But what we can say here is, oh, I normally like to write a note. Now I'm writing this in green to say you don't have to write this. But I said assume that it's going this way, therefore clockwise. What we can see here is that this was wrong. Our assumption was NG. That's common to use in practice for no good. It means if calculation fails, we'll write NG. Assumption is no good, therefore anti-clockwise, therefore pulling out, right, going back into the direction. So therefore we can say RAH equals 1,500 newtons direction that way. We're all okay with that? Now, obviously there's something that comes with, the experience that comes from doing this for many, many years, right? But there's a point where I literally could have done this question. I mean, I certainly knew the direction without thinking about it, and I pretty much could have, I could have done this question very quickly. I wouldn't have needed to show nearly as much working out. For you guys, I'm going to stress, it is a good practice to write the working out. You want to, rather than taking shortcuts, part of what you're doing here is demonstrating your answers. As professional engineers, you have to document everything because several people will be verifying your work. Other people, your boss, and probably another person in another office will look over your work and they will need to see that you have clearly explained what you're doing, right? And that is just as important for the markers. It's very easy to get one of these signs wrong. It's very easy to leave out a force and make a silly mistake. The more work that you can show the marker, the more that they can give you. So, okay, we've now got our RAH and RAV. Okay, the next part of this question is that we need to figure out the angle. Now, I don't have a calculator out, so I'm going to ask people to help me out, but I will take some estimates of things. If I have my component forces 500 up and 1500 along, right? RAH and oh sorry, I got that wrong one. Okay, I can't do that question in my head, so I'm going to need help on that. I can tell you that I know that because this is a right angle triangle, and that's a hypotenuse, I know that RAV has to be bigger than 1500. Right? It's probably going to be less than 1800, so what's the number?
1581.
Okay. 1581. That sounds pretty good. Now, the next thing is we have to show an angle. If you show the angle just as theta, the mark will be fine with that. Now, actually, I think that if we go back to the HSC question, I just have to...
Yeah.
It did just ask for horizontal and vertical. That's great. So they saved us some time. We're going to continue the question just a little bit, just to, you know, because it's not unreasonable that they will ask for a little bit more of the question. Yeah, they have just asked for horizontal and vertical, but let's assume... My recommendation is that we always measure our angles measured from the horizontal, right? So we measure the angle from that distance. Or if it's the angle is going down, you measure the angle that way. That's what I would do, right? And I draw an arrow to indicate the angle. That's what I would do. It's up to you, obviously, how you approach that. The marker probably will not mark it wrong if you do the other angle, if you do the obtuse angle. Okay. To figure out this value, theta equals arctan, which is opposite over adjacent. What is that value? Now again, I can tell that angle is going to be less than 45.
18 degrees.
18 degrees, substantially less. Okay. Now, for me, I would give my answers in degrees, but if you gave the answers in radians, the marker will not be happy. They'll have to get a calculator out, but they will be able to answer the question correctly. Okay. I don't know why I did all of that in red. I guess that it's not part of the question, so we can move on to the last. Now, the next thing we're going to do is we're going to find this force here. Now, to do that, this is pretty easy, right? I think they've given you a pretty easy question, and I think for full marks, you really couldn't ask for questions that were, you know, easier than this. What I'm doing is I'm drawing my cut. It is a good idea to show to the marker where you have made your cut for a section. Yeah. So what I've done is I've cut my section here, and I'm going to label this just for the sake of convenience. I'm going to label this one Z. Right? Z's a bad letter, but okay. Now, when I do that, when I make that cut, I now create two new internal forces. I don't do internal forces for everything. I just do the internal forces for the members that I've cut. Remember that if you're cutting more than 3 members, you're going to have a bad time. Now, we have been asked to find X, Y, and YZ. well, we haven't been asked to find YZ, we've been asked to find XY. But we've exposed, by cutting through the member, we've got two members. One is our target. That's the thing we're finding. This is an unknown. Now, what we want to do is we want to find some way of eliminating the unknown. Now, first of all, I'll start by saying I've made an assumption here. I've made an assumption that it's both of these arrows are pulling out of this node. Right? What that means is if you look at where the thing starts from, where it joins, that both of them are in tension, which means that the arrow is pointing away from the node. The simple version of this is this force is tension, this is compression. Here we can see both of the forces, the internal force is pulling out of the node, here the internal force is pulling into the node. Right? So, the question here is we have two different options. We have what I call the lone wolf or the meetup method. If we have two unknowns, now in this case we only have one unknown. If we have two unknowns, we eliminate them through using the magic of moments, and we find out where those two forces meet. Once we know where those two forces meet, we use the magic of moments to eliminate them. Right? We don't have two unknowns here, so instead we're going to look at the other alternative, which is what I call the lone wolf method. The lone wolf method says that only this force here, our target, is the only member that can resolve a vertical force. We have a vertical force here, 500. We know that force. The only thing that YZ cannot take a vertical force. It is horizontal. It has no vertical component. It cannot take vertical. It just can't. So XY is the only force the only member that can resolve a vertical component. So what that means is, if we have 500 down, it has to be balanced by 500 up. So I'm drawing that here. If we have 500 down, means we have to have 500 up, and the only way we can get 500 up is through X, Y, V, the vertical component. And if we have XYV of 500, if we have XYV equals 500, then what force in order to provide 500 newtons up, how much total will it have to provide? How much total will it have to provide? It's obviously going to have to be more. XY total is going to have to be more than XYV and XYH. Okay, what is the angle of this member? 45 degrees. We know that because it's 1 meter by 1 meter, so we've got 45 degrees. Now, we can use trigonometry, right? I'm going to go through that very quickly. SOHCAHTOA. I should have done that in green. Okay, we are trying to find the hypotenuse. The only value we know is opposite. So, we're trying to find the hypotenuse, and the only value we know is the opposite. So we're going to be using SOH, which is sine theta equals opposite over hypotenuse. Now we want to find the hypotenuse. I'm going to jump a step in algebra here, and I'm just going to assume that you can go that hypotenuse equals the opposite divided by sine theta. Which means that xy, we're back to our equations now, xy equals 500, or let's actually go back a step, xyv divided by sine 45. Well, actually, you know what, if we're going to go back a step, let's go back a step. Sine theta, which means that 500 divided by sine 45. Now, I know that sine 45 in this case is we're going to get this number here is going to be 1.41, 141% of 500. So it's going to be about 700. Can someone give me that value?
Yep. 707.
xy equals 707 newtons. Now,
That's a short point.
this question has told us that it's in tension. But let's just check on that. See how here we have our arrow going up, and see how here we have our arrow going up. That means that our arrows match, the arrow that we found matches our assumption. What was our assumption? We always assume we're going to pull out, we always assume, it always makes us tense, right? That tension, right? We assume tension. If we assume tension and it matches our assumption, it means that this was in tension. Now, for 2 marks each, that's pretty generous, right? These days, you probably have to do more for that mark. They probably ask you to calculate the angle, or they'd ask for a more difficult question to do that. Yeah?
Is XZ, is that a zero force member?
The zero force member? Okay, so that's a really good question, something worth talking about. We can have zero force members, right? If we look at this diagram, if they said to us XZ here, right? If they said to us, just looking at that diagram, we can assume straight away, we don't need to do any calculation whatsoever. We can see that because if we zoom in on this node, right? I'm going to use green because if we zoom in on this node, what we have here is we have 3 forces. I'm going to use red for forces. Okay, we have a force here, we have a force here, and we have a force here. Now, we know that this one here is going to be 500 going out, right? Just because it's an isosceles triangle, 500, 500, right? So I know that that one it's pulling out of the node, so it's going to be in tension, so it's going to be pulling out of the node here in tension. In order to balance that force of 500, this one here will also have to be going out, balancing at 500. Yeah?
Yeah.
Am I happy with that? Now, let's assume that this had 1 Newton of force down. Just 1.
Yeah.
Well, let's go with a better number just so that it looks better on the screen. 4 newtons, right? Because 1 doesn't, not very clear. 4 newtons going down. What balances those forces in this node? What balances those forces? There's nothing that could balance. There's nothing that provides an up to balance that. Yeah? So therefore, the only number that is acceptable there is 0. Now we're just going to imagine, we're in imagination world, that someone put 30 newtons here. They applied an external force of 30 there. Now what would happen? There would have to be 30 going up in order to balance that force. Now that's not what happened, right? Enough imagination for you, right? That's not what happened, but that tells us that there's a 0 force member there, right? And we're allowed to write for our working out. If there's ever a question that the trial or the HSC that asks to find 0 force members, it's happened. I've certainly written them, right? What you can then write is you can write your answer. XZ is 0 newtons by observation. Right, 0 force member by observation, and that is fine. You're totally allowed to do that. So it's an excellent question. I'm really glad that you brought that up. Now there is more that we could do for this question. If we really wanted to suck this question of all value, we could find our reaction B, but we saw that we didn't need to. We saw that we didn't need to. Alternatively, if you really wanted to, test out your skills, right, you could find reaction B and then check that the sum of all your forces horizontally matches your expectation, right? You could do that. You could calculate, so if you wanted to do extra work, you could do sum of the moments about A equals 0. That will find for you RB equals something. And then you'll have to see if RB equals something when you match sum of the forces horizontally. If those two values for RB match, then you know that you've done it correctly. An alternative thing you can do is, if you're really keen, is you could do this truss, except instead of cutting it and taking to the left, you could cut it and take it to the right. No, sorry, mix up those values. You could take your truss like this. Now, that's much more difficult because you have all of these extra forces you need to worry about. But you were allowed to do that. I said yesterday, you're allowed to take left or right of the truss. Right now, when we do that, we don't count any of these internal members. Right? All we care about is the members that have been cut by our section line. We've drawn this section line here. That is all we use. When we use the method of section, we just cut it and we take the members from there. That's it. Right? These ones, the members that are cut by the section line, we assume are in tension. Now, it doesn't mean that we actually think they're in tension. It just means we start from the position that they're in tension, and if our answer is wrong, we'll get a negative number. Like we did here with ROH, that we found that it was, in fact, going the other way. Which is why I corrected it there. Right? When we get a negative answer, we know that our assumption was no good. If our assumption was no good, we change our direction. So that's what we do here. Okay, so that gives you a little bit more work if you wanted to. If you wanted to discover every member, so another question you could do if you're interested is you could find, we've already found this one here, we called XZ. You could already find XZ, but you could also find, to make the question, we've already found also BZ, but what would be interesting is finding out what BX was and what AX was. They're two extra questions. Also AB, there's some more members if you wanted to keep pressing that a bit further. Okay. If you find these questions and you want to do more work, you've run out of truss questions and you really want to do more truss questions, what you can do is you can take this question and put it in the Johns Hopkins Truss Analyzer, and that will give you your answers, and that will tell you if you were right for questions that you don't have answers to. And so that way you can get a lot more questions. Okay, I will pause this recording and then I will go on to the next one. It's okay.